Hello, everyone. In this lesson, we're going to be taking a look at bond character and polarity. So what we're looking at here with bond character is the degree to which electrons in a chemical bond are shared or transferred. So generally, we usually describe chemical bonds as either covalent, where electrons are shared between atoms, or ionic, where electrons are transferred between atoms to form ions. But it's really not quite that simple. There aren't really any covalent or ionic bonds per se. These are all just electrostatic interactions between positive and negative charges. So we need some way to quantify bonds in a chemical bond are shared. And generally, this is done by looking at electronegativity difference between two bonded atoms. So bond character, let's say it can be surmised from the electronegativity difference between two bonded atoms. So I have three different chemical bonds here that we're going to take a look at. A hydrogen-hydrogen single covalent bond, nitrogen-hydrogen single covalent bond, and then we have an ionic interaction between potassium and chloride ions. And what we're going to do here is look at the electronegativity difference between the bonded atoms in each case. And this can be found on your periodic table, looking at the electronegativity values on your periodic table, which are given in units of Pauling, or the Pauling unit, named after Linus Pauling. So if we look at our periodic table, let's color code this at hydrogen. What we find is that the electronegativity of hydrogen is 2.20 Pauling unit. And in this case, the difference between the two bonded atoms for a diatomic hydrogen bond would be 0. So we're going to call this delta En for difference in electronegativity. So delta En for that HH bond is very simple, 0. Each atom has the same electronegativity. If we take a look at the nitrogen-hydrogen bond, so we had 2.20 Pauling for hydrogen. At your periodic table, look at your periodic table, you'll see nitrogen is 3.04 Pauling. So we do the difference between the two. In this case, we get a delta electronegativity, or difference in electronegativity, of 0.84 Pauling. And then finally, we'll look at our KCl interaction over here, bond between potassium ion and chloride ion. So we've got chlorine with an electronegativity of 3.16 Pauling, according to our periodic table. And potassium is 0.82 Pauling. And that gets us an electronegativity difference of 2.34 Pauling. So we see three different bonds here, three very different magnitudes for the difference in electronegativity. And as I said earlier, we can determine the bond character of each of these three chemical bonds by looking at the electronegativity difference between the two bonded atoms. So how exactly are we going to do that? Well, the greater the electronegativity difference, the more unequally electrons in the chemical bond are shared, as a general statement. So let's write that out here. Oops, let's not do that in green. Just to keep our color codes consistent here. Let's go back. There we go. So greater electronegativity difference is going to indicate a more unequally shared pair of electrons. So let's write it this way. The greater the electronegativity difference, the more unequally the electrons are shared. Or another way of saying unequally shared electrons, maybe we could say the more ionic that bond would be. Covalent bonds would be equally shared electrons. If we're talking about a true covalent bond, those electrons are shared equally. The less equally electrons are shared, the less covalent that bond becomes. And as it becomes less covalent, it becomes more ionic. So think of this sort of as a scale. So because there are similarities between bonds with similar electronegativity differences, we have categories that we use to describe the degree of equal sharing or unequal sharing of electrons in chemical bonds. In fact, each of the three molecules, or not all of them are molecules, sorry, but each of the three bonds, rather, we're looking at individual bonds. Each of the three chemical bonds that we're looking at in our example fall into different categories based on their electronegativity difference. So let's talk a little bit about these categories. And let's start with the hydrogen diatomic molecule over here with an electronegativity difference of 0. This is what we refer to as a non-polar covalent bond. So this would be the most equal sharing of electrons that we're going to see for a pair of bonded atoms. Now, it'll be equally shared in the case where we have a diatomic molecule, homonuclear, meaning that both of the bonded atoms are the same element, as we see with diatomic hydrogen. That would give us an electronegativity difference of 0. But other bonds with very small electronegativity differences also can be classified as nonpolar covalent. The electrons might not be shared equally, but they're very nearly shared equally in cases where the electronegativity difference between the atoms is low. So what is the threshold here for nonpolar covalent? We're looking at differences in electronegativity that are less than or equal to 0.4 Pauling. That is how we are going to quantify the nonpolar covalent bond. And that's what we see with the diatomic hydrogen molecule. So let's look at our second example here. We had a hydrogen-nitrogen bond with a higher electronegativity difference. It wouldn't fall into this first category of nonpolar covalent because its electronegativity difference is greater than 0.4 Pauling. So what do we call this type of bond? Well, it's referred to as a polar covalent bond. So here, the electrons can still be described as being shared, but they're not shared equally. One of the atoms in the chemical bond has a greater attraction for the electrons than the other. And what we're looking at for polar covalent electronegativity differences that are greater than 0.4 Pauling, but less than 1.7 Pauling. So somewhere in this range of 0.4 to 1.7 Pauling for the electronegativity difference. We would describe that bond then as a polar covalent bond, like the NH bond. Our final example, we had what we know to be an ionic bond, KCl. We've seen this before in our discussion of ionic bonding. We know electrons are transferred here. The electronegativity difference is very high as a result, 2.34 Pauling. So this would be classified as ionic. And what we're looking at here for ionic bonds typically would be electronegativity differences that are greater than 1.7 Pauling. Now, you could make an argument for some categories that are intermediate between these three examples. So we could say things like mostly covalent or mostly ionic. But for the most part, in describing bond character in honors chemistry, we're going to stick to these three classifications. And we're going to quantify them, as I have shown here, with nonpolar covalent bonds having an electronegativity difference less than 0.4, less than or equal to 0.4 Paulings. Polar covalent bonds being somewhere between 0.4 and 1.7 Pauling, and then an ionic bond having an electronegativity difference greater than 1.7 Pauling. So that's the guideline that we're going to use to classify bond character. Now we're using this word here, polar, so it's worth talking a little bit about polarity in our discussion of bond character. So let's look at polarity. When we use this word polarity or polar, we are talking about a separation of electric charge, specifically a separation between positive and negative charges. And this can be quantified with what we call a dipole moment or an electric dipole moment. So this is an actual measurement of the degree of separation of positive and negative charge between two bonded atoms. And this is measured in the SI unit in units of centimeters, or excuse me, centimeters, coulombs rather. Coulombs times meters. Coulomb is the unit of measurement of electric charge. Of course, you know meter, a unit of measurement of length. So we have coulombs times meters. That would be the SI unit of measurement of electric dipole moments. But another common unit of measurement is the debye. So this is something that you might see if you're looking up dipole moments, electric dipole moments for different chemical bonds or molecules on the internet is the debye. And this is typically just a capital letter D. As its label. So something to be aware of. We won't really quantify dipole moments in this class, but you might be presented with data at some point. And it's good to know what this is, what we are measuring. We're measuring the degree of separation between positive and negative charges. We're going to use dipole and polarity sort of interchangeably for the most part. It's not necessarily appropriate, but they do, for our purposes, reference the same basic phenomenon, this phenomenon of separation of charge. So going back to the two bond classifications that we had previously, we had nonpolar covalent and polar covalent. We talk about a nonpolar covalent bond, so that was an electronegativity difference less than or equal to 0.4 Pauling. In terms of separation of charge, we don't really have any. So electrons are shared equally, but I'm going to put a qualifier in here. So we're going to say electrons are mostly shared equally. And as a result, there would be no dipole moment for a nonpolar covalent bond. So we say mostly shared equally here just because we are looking at electronegativity differences that are less than or equal than 2.4 Pauling. So there is going to be, for some of these nonpolar covalent bonds, some degree of unequal sharing, but it's small enough that we don't really have a significant dipole moment. Okay. Now, on the other hand, if we have a polar covalent bond, electrons are going to be shared unequally. And as a result, these polar bonds will have a dipole moment. Now, not all polar covalent bonds are equal in terms of their electric dipole moment, and it's going to be based in part on electronegativity difference. If you have a higher difference in electronegativity, you can expect, with all other factors being equal, to have a larger electric dipole moment and a greater separation of charge as a result. So we will take a look at this in greater detail a little bit later on in Chapter 8 as we start to look at things like solubility, as we start to look at molecular polarity and intermolecular forces. But I want to give an example before we finish up our discussion here for today of looking at a polar covalent bond. And we're not going to quantify the electric dipole moment, but we're just going to sort of look at what that might mean or how we might sort of visualize that in terms of a Lewis structure. So the example we're going to use here is a HCl bond, so hydrogen and chlorine bonded together here. If we look at our periodic table and record the electronegativity values here. We're going to get 2.20 Pauling for hydrogen and 3.16 Pauling for chlorine. So that would be a difference in electronegativity of 0.94 Pauling. So that is going to classify then as a polar covalent bond. It is greater than 0.4. It is less than 1.7. So we have a polar covalent bond. But what does this mean? What is the result, or what is the implication of the polarity of this bond? Well, chlorine has a higher electronegativity than hydrogen, which means it has a greater attraction for the shared electrons in this polar covalent chemical bond than does hydrogen. So chlorine has a stronger attraction. It's going to pull with more force on those electrons, and the electrons, as a result, are going to be closer to the chlorine in this HCl bond than they are to the hydrogen. And that creates that polarity, that separation of charge. And while we won't actually calculate and quantify electric dipole moments in this class, what we will do is indicate separation of charge in one of two ways. The first is using lowercase Greek letter deltas to indicate a partial charge. So this is not like an ionic bond where electrons are transferred from the hydrogen to the chlorine, but the chlorine does have a greater attraction for the electrons, and they're closer to the chlorine nucleus as a result. So that's going to cause the chlorine to take on a partially negative charge. Not a negative charge. There's no transfer of electrons here, but there's enough separation of charge that there will be a partial negative charge on this end of that chemical bond, on this end of that molecule. And that's going to leave the hydrogen then with a partial positive charge. So we use these lowercase Greek letter deltas and then the sign of the charge to indicate where the electrons are more concentrated. So we're going to have a higher concentration in terms of the shared electrons of negative charge over here on the chlorine, getting it a partially negative charge, and then a lower concentration of electrons near the hydrogen, which gives that end of the molecule a partially positive charge. So we can indicate the polarity of this bond with these lowercase Greek letter deltas. Another thing that we can do is use an arrow notation. So in this case, we actually draw an arrow pointing in the direction of the more electronegative element, which is chlorine. And then we draw a perpendicular line through the opposite end. So it looks like a positive sign, right? And this achieves the same thing as the lowercase Greek letter deltas, showing us that the end of the molecule where the chlorine is located is going to be partially negative or take on a more negative charge, and the end of the molecule where the hydrogen is located is going to be more positive. So two different ways of indicating an electric dipole moment qualitatively. This is not quantitative. We're not actually giving a numerical value for the dipole moment here, but we are indicating that the dipole moment exists for this particular molecule. And we can do this for all polar covalent bonds. And it's going to be useful to us a little bit later on when we look at molecular polarity.